Hi all. In this video, we see a paper titled Robust PID Steering Control for Automated Driving from Istanbul, Turkey. So, this paper attempts to develop a PID controller, especially steering control for automated driving, based on some stability characteristic utilizing the linear and nonlinear models. So in recent years, there has been many attempts to develop level 3, level 4 vehicles, and also people are attempting to bring a level 5 vehicle into the picture. So the level 5 vehicle required to do an automated steering and also automated pedaling and braking. So there has been many attempts to develop an automated speed control and steering control. One among the method is you use the PID based type controller for the steering and controlling the vehicle's lateral dynamics. So there has been many attempts on one among the reason for us to develop the steering control. The definition of the steering control is to minimize the yaw error and also to minimize the lateral deviation of the vehicle from the principal lane. So there has been many attempts to develop like a kind of a nested PID controllers. One is to minimize the yaw error, and another one is to minimize the lateral deviations. So in this paper, they try to attempt to develop a PID based on the parameter space approach. The meaning of the parameter space approach would be to use the dynamics of the vehicle, maybe a linear or non-linear, which is as realistic as possible. Then they try to identify the stability characteristic of that developed systems. Based on the developed stability characteristics of the developed system, they try to identify the zones for the KP, KD, KI values where the system would be stable forever. So in this paper, what they did is they try to make two free parameters instead of three parameters. One parameter is fixed, like Ki value, and the gain Kp and derivative gain Kd values are being computed based on the D stability requirements. So this was the overall ideas of this paper, and for that it requires some kind of um, uh, a very approximate linear model or a nonlinear model. So linear model is defined by these equations one, so which not necessary to go deep into that. Maybe we can see it later. What is the beta? All these values are something related to the dynamics of the vehicle. So this is the linear model, and this is the non-linear model they have taken into account, where the non-linear model has some kind of a lateral two accelerations like translational along x and y, and also rotational accelerations. And these are the force acting, and these are the definition for the forces. For example, is the aerodynamic force, the gravitational force, and this is also rotational accelerations, and this is the moment of inertia. So these are the characteristic equations that have been developed for these systems, and based on that things we utilize to develop. For example, for a linear system, they try to make characteristic equations in a frequency domain using a Laplace transform, where n is the numerator, d is the denominator, and based on that they identify what is the characteristic based on the for the PID closed loop system equation 17. It can be entered into a polynomial equations of nth order. The nth order is based on the characteristic of the systems, and they define that it has to be d-stable like this, real and imaginary part of the numerator and denominator. What should be this bounded domain will define the stable region for the dynamics of the systems. So there are three characteristics they identify. One of the requirement would be that imaginary part of this has to be zero, that is called as complex root boundary. Another one is the a0 has to be zero, that is called as real root boundary. Another one is a plus, and the highest order coefficient has to be zero, that is called as IRB. So based on this, these three parameters have been defined and identified using the stability criteria, and that can also be visually depicted in the equation 8. So our characteristic would be to map this bounded this boundary into a parameter space using this into this space and try to see what are the values for Kp and Kd, so that the system becomes stable. So they have used this 1789 developed equations to map this bounded domain D1, D2, and dt into the parameter space, and assume that this is the our for automated steering control, this is the linear dynamics, and this is what they developed in a transformer space. And based on this, they have developed robust destability criteria has to be developed. Here there are they have taken only the two values, the k, here the k is value is fixed and selected to be 5. And if you see in the figure uh, 10, and this is what the kpkd values, and this is the stable region they have identified for the given dynamics of the systems. So these are these boundaries are based on those equations that we have explained earlier, 17, 19, and 20. So once this bounded domain for the kp and kd values are be identified, we are choose the parameters so that it becomes stable. And based on that criteria and analyzing the again the 11 is similar to 10, but on addition they have some kind of a numerical values in the x and y axis, and based on this criteria they choose this red cross mark as seems to be the value required based on some additional empirical analysis, and they decided that kp and kd value to be 15 and 12.5 respectively. And they also did two simulations. One is following a path consisting of a straight track of 1 meter, followed by a full turn in a circle of a radius of 100 meter, and also additionally followed by another 1 meter, 150 meter straight track, using speed around expecting the speed around 50 meter per second. and and the second test would be something to vehicles try to follow a curved path with different road curvature values, and the speed they expected to be maintained keeps change has to be changed between 5 to 18 meter per second. And once since we are only controlling the steering, the speed would be controlling a different independently. So they have seen and charted the values, and 13 gives a summary of these two simulations just, and what based on that analysis it could be able to follow the expected thing, and expected the track error like yaw error and the lateral deviations error are kept minimized in both the simulation tests based on these results summarized in the figure 13. So what conclusion is, this paper attempted to develop a robust and destabilized model-based PID steering controller for automated steering, and they tested in simulation tests. It seems to be promising, and they will be implemented in the experimental vehicle that has been defined earlier, which I haven't described. And most of the attempt here in this paper is to explain what is a destabilized PID control for the automated steering. Thank you.